Prior to 1905, it was pretty much universally accepted that light is a wave. But then in 1905, Einstein comes along and says that, yeah, light's a wave, but it also has a particle nature associated with it. Waves have a particle nature. Fast forward a few years, 20 years or so, and a guy named Louis de Broglie, it's pronounced de Broglie, it's written de Broglie, a Frenchman, suggests that if waves can have a particle nature, then why can't particles have a wave nature? It's an argument based on symmetry, purely on symmetry. Physics is a very symmetrical subject. If A will cause B, oftentimes B will cause A. If waves can be particles, then maybe particles can be waves. At the time, he had no evidence to support his hypothesis. But over the years, over the last 80 or 90 years, we've established evidence that supports the de Broglie hypothesis. In fact, particles like electrons, really, really small particles like electrons, do in fact have a wave nature. In fact, an observable, in certain cases, an observable wave nature. Let me just summarize what we just said here. The de Broglie hypothesis says that if waves can behave like particles, in other words, if waves have a particle nature, then particles, I'll say like electrons, we're talking about really, really, really small particles here, not talking about things like cars, although technically you could argue that there's a wave nature associated with them. It just wouldn't be any kind of wave nature that would manifest itself because of the mass of the car. Talking about really, really small things like electrons can have wave nature. Now, we said a minute ago that over the years, over the last 70, 80, 90 years, there's been evidence to support the de Broglie hypothesis. That evidence comes through what we call diffraction experiments, electron diffraction experiments. I'm going to real briefly describe what I mean by that. Think back to the Young's double-slit experiment. This is diffraction and interference of light, of EMR, usually visible light, but could be any kind of EMR. We got two openings. The wave, the EMR, goes through both of those openings, behaves like a wave, diffracts, interferes with itself, and produces an interference pattern on the screen on the other side that looks like this: bright spot, dark spot, so on. And nothing new here. This is exactly what we did in our last unit. You guys did a pretty good job on this part. But now what happens if we don't shine EMR through those two openings, rather we shine electrons through those two openings? Don't copy this diagram down quite yet, this second diagram. What would we expect to see on the other side? Well, let's picture this as something bigger than electrons, something that we can actually visualize. Like, let's say we got two doorways here, and we're tossing baseballs through one at a time. There's a metal wall on the other side that will dent wherever a baseball hits it. Okay, if you're a baseball fan, it's the Green Monster in Boston. Okay, it gets dented every time a baseball hits it. Baseball goes through either this opening or this opening and causes a whole bunch of dents right there and a whole bunch of dents right there, right? Yeah, but that's not what happens with electrons. If we fire these electrons through one at a time, then we see these electrons forming a spot on this wall back here that ultimately, eventually, if we shine enough of these electrons through there one at a time, will form a pattern that looks like this. It forms an interference pattern. And we shone one electron through at a time. So what happened there? The only explanation possible is that the electron behaved like a wave, went through both openings at the same time, diffracted, interfered with itself, and produced an interference pattern. Therefore, electrons and small particles like that have a wave nature. Evidence for the de Broglie hypothesis that, hey, if waves can behave like particles, then particles like electrons can behave like waves. Now I'm going to point out one more little thing which you don't really have to know, but just to get your mind kind of going a little bit here. If this seems a little bit wacky to you, what I'm about to say to you should seem really, really wacky to you. This happens. Okay, this has been observed thousands of times. But what's also been observed is that if we do something to try to tell, to sneak a peek at which hole the electron went through. Remember I said it has to behave like a wave and go through both holes at the same time, diffract, interfere with itself. If we try to sneak a peek at which hole it goes through, guess what happens? Yeah, it chooses a hole. It chooses an opening at that point. If we try to observe, then it chooses one hole or the other. In other words, it behaves like a particle. The wave function, we say, collapses, and it behaves like a particle, and it goes through one opening or the other. And what do we see? Those two spots on the other side. So the simple act of observing it, whether we try to observe it with our eyes or some kind of electronic measuring detection device, doesn't matter. Any way that we try to detect which hole it goes through causes the wave, which forms this pattern, to collapse and ends up forming this pattern. Like, that's wacky. Okay, if this wasn't crazy, that an electron can diffract and interfere with itself, to me, this is way crazier. That when we look at it, the wave function collapses and now it starts behaving like a particle. But that's the only explanation we have for it. Okay, that's what we see. We've observed this thousands of times, and that's the only explanation that we have. Okay, it behaves like a wave. It interferes with itself until we try to observe which hole it goes through, and then it picks one. Somehow decides to pick one or the other. What's the big takeaway here? De Broglie said electrons can behave like waves, and we know that that's the case because of electron diffraction experiments, period. This leads us into our last and currently accepted model of the atom, which called the Schrodinger or quantum mechanical or electron cloud model of the atom. Remember, we have the Dalton solid sphere, we have the Thomson-Reisenbund model of the atom, the Rutherford planetary model of the atom, the Bohr, it's called electron level model of the atom, and now we have the Schrodinger quantum mechanical electron cloud model of the atom. It says that, in fact, there is a small, dense, positive nucleus. Now we know there's protons and neutrons in it. And surrounding that nucleus is mostly empty space, but there are electrons orbiting around that nucleus. But unlike Bohr, who was so sure of where those electrons were, Schrodinger said, no, we can't be sure. It's not like that Schrodinger took a step back and said, wait a second, I'm not sure where they are. You're positive, I'm not so sure. Like, Schrodinger is sure that we can't know for sure where they are. And why can't we know for sure where they are? Because it's not really a particle. It's a wave. The electron's orbiting around the nucleus as a wave in its wacky way. Now, we try to observe where this electron is. The wave function collapses. We'll find a spot. But where are we going to find it? We don't know. The most probable location that we'll find it is where Bohr said it was going to be, the Bohr radius. If this is where Bohr said it was going to be, that's the most probable location for it. But there is a real possibility, a real probability that it could be somewhere else. Kobe, where's Mrs. Staffichuk right now? Probably in her office. How sure are you of that? 80% sure? It's funny, the person this morning said 80% too. 80% sure Mrs. Staffichuk's in her office. Is there a chance she's somewhere else? Yeah, there's a 20% chance she's somewhere else, right? She could be in the atrium. There's a pretty good chance she's in the atrium, like maybe 10 or 15%. Maybe she's down in the math wing teaching a class. There's a smaller chance of that. There's an even smaller chance that she's outside. There's an even smaller chance that she went home because she forgot something she needed this afternoon. There's an even smaller chance that she had to go to Calgary to take care of something for commencement, or prom. There's an even smaller chance that she's just had enough and went to Mexico this morning after announcements. The odds of her being in Mexico are pretty small, right? But they're not zero. Okay? They're not zero. The most probable location that we will find her is in her office. But there is a real possibility, albeit a small possibility, that we could find her as far away as Mexico or even further. The most probable location we'll find the electron when we look for it is where Bohr suggested that it was. But there is a real possibility that we'll find it anywhere within that cloud. And the cloud extends. It just becomes less dense as you get further away. So there is a real possibility that we'll find the electron way the heck over here. Which is a really, really, really small possibility. That's all. That make sense? We still got electron levels. They're still characterized by certain energy. It's just that their position isn't as predictable as we thought it was with the Bohr model of the atom.